Shalom lekulam. It is my pleasure to introduce our guest speaker today, Ariel Ismach. Ariel is a materials engineer from Ben Gurion University, and he did his MSc and PhD at the Weizmann Institute of Science in the group of Ernesto Isilevich. Obtained the PhD in 2008, right? And at the same year, he also received a PhD student prize from the Israel Chemical Society for developing novel approaches for the guided growth of carbon nanotubes. And immediately after that, he moved into California, UC Berkeley, and Lawrence Berkeley National Lab until 2008. And after that, he moved into Austin, Texas, to work with Rodney Ruoff. And Ariel's research interests include synthesis and characterization of atomic thin materials, growth mechanisms, and rational growth of atomic films composed of different 2D atomic materials. And Ariel will tell us about his work. Thank you, and the podium is yours.
Thank you, Ilan. Thank you for the invitation. It's a pleasure to be here. So my name is Ariel Ismach. I will be talking about, in general, the synthesis and characterization of 2D atomic materials, specifically graphene and hexagonal boron nitride. But first, I will give an introduction on 2D atomic materials, why these materials are so interesting, and why so many people are working currently on the synthesis and characterization and application of these atomic films. Then I will move to the description of our work in graphene and hexagonal boron nitride, growth mechanisms and characterization. And I'll conclude, and then I will describe my research plan briefly, what I think it is interesting to go on and continue research. I'll start by saying that these materials are not new. 2D atomic films and 2D atomic materials are not new. These materials are sometimes called van der Waals solids because the in-plane bonding is a very strong covalent bonding, but the bonding between the layers is van der Waals, relatively weak van der Waals. And these materials are very interesting for a wide variety of reasons, and there are many different materials I will show you in a minute. And here you can see the three main methodologies that people during the past 30 years were using for studying these materials. The first one is graphite intercalation compounds, in which they introduce molecules and different materials in between the layers of graphite and also other layered compounds. And the reason that they did that is to achieve different properties not existing in the intrinsic properties of graphite, like superconductivity or magnetivity. Another way that people were using from the 70s is the so-called today the Scotch tape method, in which you take a sticky tape, and by that you try and isolate few layers or single layers. Today people manage to do it at the single layer level with graphene. And people had some success in isolation of a few layers of different layered compounds, and then investigate the different properties as a function of a number of layers. And the third method was the physical and chemical vapor deposition methodologies. And in this method, the achievements were relatively thick films, and usually they were composed of a mixture of different phases, like turbostratic, amorphous, hexagonal, cubic, etc. So as you can see, by any of these methods, there is no option that you can achieve a control over the single layer level or few layers level, and then characterize them as we are trying to do today, by the methodologies that I will describe in a few minutes. Here you can see a list of different layered compounds. It's a partial list with different properties. You can see that we have semiconductors, semi-metallic, metallic compounds, and many of them are in the sweet spot for many electronic and optoelectronic applications. And more interesting is that there are a few theoretical papers showing that you can, in principle, change the band gap and the intrinsic electronic properties of these materials by applying strain or electric fields. And moreover, some of these materials, like MOS2 and tungsten disulfide, change from indirect band gap materials in the bulk to direct band gap materials at the single layer level. So as you can see, there is a lot of variety and diversity with these materials and properties that you can achieve by the intrinsic properties and by the isolation to the single layer level. So then you can, in principle, think of many applications that you can achieve with these materials in nanoelectronics, transparent conductors, transparent devices, NEMs, nanoelectromechanical systems. These materials are in principle atomic materials, so they are very sensitive to the environment, so they can be used and were proved to be very good sensors, very good sensitivity. And in the bulk regime, you can use them as in batteries and composite materials to achieve many different applications. So then I will move directly to graphene. So why graphene is so interesting? Graphene is an atomic layer of hexagonal lattice of carbon. It has a very unique band structure with a linear dispersion, energy momentum dispersion at the K point that make the electron behave as a massless particle. It is unbipolar. It has a ballistic transport over hundreds of microns, huge mobilities. It has very good thermal conductivity at the in plane, but very weak thermal conductivity perpendicular to the layers. It is very strong. In principle, the physical properties can be tuned, can be chemically tuned, and it can be used by. So then you can think of many applications again in electronics, thermal management, from the nanoscale to the macro scale, NEMs, batteries, sensors, and transparent electronics, transparent and flexible electronics. So a bit about the history of graphene. As you can see here, the number of publications as a function of the year. You can see that in 2004, when Professors Novoselov and Game from Manchester published their beautiful work on the electrical properties of single and few layer graphene, you can see that the growth in the number of publications is exponential. But in fact, graphene was, as you can imagine, was present and existed even before that. In fact, in the 70s, early 70s, graphene was identified to appear as a single layer on single crystal transition metals by May from Cornell, then on silicon carbide. Then it was attempted to isolate it by different mechanical exfoliation techniques. And then the Manchester group did their work in 2004. But then it took 5 years to find a way to synthesize in a consistently manner a single layer graphene over large areas. And it took actually from 2009 till today, actually only today we can grow single layer graphene with electrical and physical properties comparable to the exfoliated graphene. And when you look at the different methodologies that are available to make graphene and to make graphene samples, you have here the quality of the graphene and the price. And you can see first that the liquid phase exfoliation is the easiest, cheapest way to do. But then, of course, you get a very large quantity of material, but with poor quality. And then the mechanical exfoliation is still the best way to get the highest quality graphene over very small areas. And then you have the chemical vapor deposition of graphene that is constantly improving. And today, as I told you, we can achieve a comparable quality to the exfoliated one. So chemical vapor deposition looks as a very good methodology to go on and continue studying the growth of graphene and other materials, as I will show you later. So how it works. The graphene is synthesized on catalyzed, in this case copper, in a tube furnace where you heat it up and you expose it to some source of carbon that can be anything, from amorphous carbon to almost any hydrocarbon that you can think of. Then after the growth, when you have the graphene-coated copper, you spin coat some polymer on it for mechanical support. Then we etch the copper away, transfer the polymer with the graphene in the bottom to the target material, and continue working with the graphene or characterizing. And so then I will now explain why on copper it just works so good and it grows as a single layer at so large scale. Here you can see a comparison of two of the most common metals to grow graphene. The first one nickel, second one copper. And in our group, we studied the growth mechanism of graphene by using the so-called carbon isotope labeling. In this case, you expose the catalyst sequentially to an hydrocarbon that is enriched with C13 carbon, and to an hydrocarbon that has a natural composition of a carbon isotope, which is 85% of C12. And by doing so, after doing so, you can characterize that by Raman spectroscopy, and you are supposed to identify the regions with C13 and C12 by any vibrational spectroscopy. So when you do this experiment on nickel, you can see that so on nickel the graphene, or the few layers graphene more precisely, grow by first the decomposition of the hydrocarbon at the surface of the metal. The carbon diffuses into the metal, into the bulk of the metal, and then it segregates out and precipitates out when you reach supersaturation or during cooling, then forming the few layers graphene. So then when you do the mapping by Raman microscopy, you can see that the C12 and C13 carbon are just mixed all together, so you can't identify different regions with the different isotopes. But when you do it on copper, it turns out that because of the very low, almost zero solubility of carbon into the copper, the hydrocarbon decomposes on the surface of the metal. The carbon diffuses on the surface of the metal, forming the graphene and then growing sequentially. So then when you do the Raman mapping, you can identify very easily the different regions with C12 and C13 enriched carbon. As you can see here by the Raman spectra. What you are seeing here in the Raman spectra is the characteristic graphitic peaks. The G, by the way, for graphene, for graphite, the G prime, and the D, which is activated only by defects.
Which one was the first?
What do you mean?
Topologically, it's not selected. Which one was the first? C13 or C12?
In this case, the C12 was first. So here you can see the domain. The first domain then was exposed to C12 to C13, which is the opposite mistake. The dark areas here are the C13 areas, and the bright areas here are the C12 areas. This is a mapping with the position of the G band. Okay, you can see that there is a shift, a very clear shift in the band. So the dark area, the shift down, is the C13 enriched area. Okay, so it was first. Sorry, it was the first. So this is the domain. Then you expose it to C12, so you get another stripe of C12 carbons attached to the domain.
Can you explain to us what those yellow rings are in the middle diagram bottom?
This one.
Yeah, what are we seeing actually?
So this is the mapping with the position of the G band. So the bright areas are close to the R represents the C12 enriched carbon, and the dark areas represent the C13 enriched carbon. Okay. But then when you look at the table, here you can see a table with the different metals that, with the most common metals to grow graphene or few layers graphene. So then you can see the three first metals, iridium, ruthenium, and copper. The three of them gives very consistently single layer graphene. And the reason for that, as I said, one of the reasons at least, is that the carbon solubility at the temperature of the growth is extremely low. Then you have the other most common materials, which are nickel and cobalt, that have a relatively high carbon solubility, and that's why it's so hard to control the number of layers with these materials, and you get usually few layers of graphene. But then you have in the middle platinum, and platinum has a moderate carbon solubility, which is enough to give you a few layers or thin graphite, but in fact it can be shown that at a very wide parameter regime you can get single layer graphene on platinum. So the question is why? And it's obvious that solubility is not the only explanation. Solubility is a thermodynamic equilibrium parameter, and it can't explain the platina case. So it must be kinetic parameters as well. Here you can see a mapping of graphene that was synthesized on platinum. Here you can see the mapping with the intensity, in this case of the 2D peak. Okay? But here you can see the same mapping in the same area with the position of the 2D peak. And you can again identify very easily the different regimes with the C12 and the C13 carbons, suggesting that the growth here is by a surface process, even though the platina has a higher solubility of carbon in it at the temperature of the growth. So, but we can also get few layers of graphene on the platina. So it's obvious that the solubility explanation, it doesn't explain, it can't explain the growth of singular graphene on platina, because it is a thermodynamic parameter, and the kinetic parameters are important as well. By the way, when you work on a platinum, you need to find another way to transfer the graphene and for characterization. And we do that by electrolysis process, in which we generate, by this reaction, hydrogen bubbles at the interface between the platinum and the graphene, which is supported by a polymer. So then the attaching the graphene layer from the platinum, and then the transfer is pretty much the same as I showed you before. Even when I see few layers, I can see the different regions. No, I guess because even when I have few layers, the diffusion is only at the just below the surface, and it doesn't reach the bulk. My explanation for that, and I'm still working on that. My explanation for that is that in the platinum case, the carbon diffusion on the surface of the platinum is much higher than the diffusion into the bulk, and that's why you can get single layer or only few layers, but you can't get in this regime thick layers as you are supposed to according to the solubility parameter. if you have a mixing. If you have a mixing. But no, if you have a mix, he's right. If you have a mix and you have a mix with 50%, let's say C12 and 50% C13, so you are supposed to be somewhere in the middle. Otherwise, you are supposed to be, the shift is correlated with the composition of, relative composition of the C12 and C13, which is related to the exposure of the different hydrocarbons to the surface, right? Then just a few words about a different system that we just finished to build and we are trying to publish, in which instead of using a hot wall system, we are using magnetic inductive heating, which is a cold wall system. And in principle, it's the same, very much the same process, but the difference is that by this methodology, we are supposed to have more flexibility in heating, in the heating of the surface, and also in local heating. So we are trying to do some kind of single crystal graphene growth as it is done in 3D, like moving the stage during local heating of the copper. But this is something that we're working on now. Now I would like to talk about some of the work that I did in Berkeley, in which I developed a way for the direct deposition of graphene on the electric materials, which is a big issue because all the transfer process from the metal causes many defects and cracks and deterioration of the intrinsic properties of the graphene by that. So in this case, I took some dielectric material, quartz, sapphire, or silicon dioxide. I pre-deposited some thin film of copper, and then during the growth and post annealing, we could show that we could by the heating of the copper, we could achieve some control over the wetting and evaporation of the copper, so then leaving the graphene directly deposited on the surface of the dielectric, as you can see here. So here is an optical microscope image of the wetting of the metal, showing a different finger structure, which is very common in the wetting of metals on surfaces. But in between the metal, you can see that by Raman mapping, in this case of the 2D, you can see that the area is fully covered with graphene. And by analyzing the graphene again, you can say that it is mostly covered by one layer, single layer graphene. And the reason that you are seeing here a small D peak is that the deposition of the graphene is not smooth, and the graphene on the surface appears to have a series of wrinkles that are parallel to the metallic structures, and these wrinkles are in the nanoscale, in the micron scale, but also in the nanoscale. This is AFM and this is STM. So then we could show that, as in every case where you synthesize large-scale graphene, you can make a series of devices and characterize. In this case, by making source and drain gold electrodes and a top gate made by ALD deposition of alumina and aluminum as a gate electrode. But more interestingly, you can use this methodology to control the dewetting and to form directly different graphene patterns on the surface without any post-lithographic step. As you can see here, for example, in these two cases, in this case copper lines were pre-patterned before the growth. And in this case, the anisotropic dewetting of the copper on C-plane sapphire was used to leave on the surface discrete lines stripes of graphene along the threefold symmetry lattice of the alumina, the sapphire crystal, as you can see here. So in between the lines here, there is no graphene. This is again mapping with the G peak here and here. So only when you get signal, you know that the graphene is there, and you can get stripes of graphene aligned along the lattice of the sapphire. I was also involved in developing a way to make large-scale nanoribbons. One of the problems with graphene, and I discussed that with Yossi Rosenbach before, is that graphene does not have a band gap, so it can be used in applications like microelectronics and logic applications. So one way to introduce a band gap in graphene is by quantum confinement. So in this method, in this case, we used a block copolymer to make a template for nano-imprint lithography with very small holes. So then we could, by controlling the fabrication parameters, we could make and fabricate a series of nanoribbons with different width. And then we, of course, characterized them electrically, and we could see an increase in the band gap. We could see that we could have control over the band gap as a function of the nanoribbon width, as you can see from these formulas. In principle, the band gap is related to 1 over the width of the nanoribbon. And this is similar to the case of the nanotube, in which the band gap of a semiconducting carbon nanotube is related to 1 over the diameter of the tube. And then the on-off ratio is related to the band gap with this formula. So then you can see that it is, of course, related also to the width. So by controlling the width of the nanoribbon, you can control the band gap and, of course, the on-off ratio of your final device. Now, we are always looking for different ways to characterize our films. The characterization of these atomic films is not trivial, and I must say that the case of graphene is pretty good, because we have a very good set of tools to characterize the different aspects of graphene and few graphene layers, like Raman spectroscopy, that works very good for graphene and not for other materials, as I will show you in a minute. But we can show also that by dark field optical microscope, we can in fact achieve a lot of information. Here you can see, so this is a submonolayer graphene that grew on a copper foil. This is just after growth. And here you can see the dark field image. This is the bright field image. This is the SEM. This is the Raman. And you can see that in the bright field image there is no, you can't detect any graphene. But in the dark field image, you don't see directly the graphene, but you see the facets of the copper that are underneath the graphene, and that are preserved due to the protection of the graphene. All the rest of the area is oxidized by exposure to air. So of course you can show that in dark field microscopy, actually the scattered light is the one that you are going to see, and you can show that if in our case, we can see that the limit of detection is about 2 to 4 nanometers nanofacet height. Smaller than that, we can't see it in the dark field. This is another area of a similar sample where you can see submonolayer growth, but you cannot see the steps. But even in this case, you can see there is a topographic edge at the edge of the graphene domain. And you can show that in Rayleigh scattering, the intensity of the scattered light is proportional to the 6th power of the diameter of the particle, and that's why it's so sensitive to very small topographic features. This is a very good question, and I can talk about that for hours, about the shape of the domains. So you can have in the growth of submonal layer, you can have domains with a 6-fold symmetry. You can have 2-fold symmetry, and this is related to the crystal orientation of the copper. That's we know. But interestingly, if you do the same process under different parameters, you get instead of these shapes, you get hexagonal shapes. If you do the same process on a high purity copper, you get hexagonal shape. And I can talk about the reasons for hours. One of the reasons is the impurities of the copper actually etches away some of the graphene, and that's why in this copper, which is less pure, you can achieve much larger domains than in high purity copper. We can talk about that later. I didn't mean to talk about that in this.
More like dendrite growth along the symmetry direction
of the crystal. Yeah, but when you use a high purity copper, you don't get a dendritic growth. You get an hexagonal growth. Small domains, but hexagonal.
Which means we are back to kinetics.
Kinetics determines the shapes of the domains, of course. So now, till now we spoke about graphene. Now I will move to my work on hexagonal boron nitride. And the reason that we are working on hexagonal boron nitride is that also hexagonal boron nitride is a very similar material to graphene in the sense that it has an hexagonal lattice with very similar parameters. The stacking order is a bit different. It's AA stacking, AA is prime stacking, in contrast to the AB stacking of graphite. It is a wide band gap semiconductor that has very nice and good mechanical and thermal properties, very good thermal conductor. And it's very stable, very chemically and thermal stable, and is atomically flat. And this is very important for electronic devices in the nanoscale, it turns out. And specifically, it was shown that when you make devices with a graphene on top of hexagonal boron nitride, both of high quality, you can get enhanced mobilities in graphene. And the reason for that is, again, that the hexagonal boron nitride is atomically flat. It doesn't have any dangling bonds. It doesn't have any surface states that can scatter the charges in the graphene. And in principle, it's also a very good thermal conductor, which is also a good thing to have in electronic devices. It was shown also that it is a good material for deep UV optoelectronic devices, and again, it's a very good thermal conductor, so it can be used for thermal management applications. And here you can see the standard characterization tools that we are using. Here you can see the first picture is an optical microscope image after transfer of the film to a silicon sample. And then you see the Raman characterization, then TEM, the Raman peak, and optical absorption. And one of the problems with this material is that there is no way, actually there is a way, and I will show you in a minute, but till now it was no way, and nobody showed a way to characterize in two dimensions the number of layers and the quality of these materials as we have tools for graphene. Raman characterization, again, for graphene is very useful for that, but not for hexagonal boron nitride. In hexagonal boron nitride, we have only one peak, and there is not much to do with it. In graphitic phase, by comparing between the intensities, the ratios, the position of the different graphitic peaks, you can get a lot of information about number of layers, quality, doping, strain, etc., but not in hexagonal boron nitride. But one thing that we notice is that we could achieve a relatively easy control over the thickness just by controlling the reaction time. So you may say that this is trivial. This is trivial maybe for classical thin films, in which if you grow them for longer times, you get thicker films, and that makes sense, but not for layered compounds. In fact, you can't grow graphene on graphite. There is no way that you can grow graphene on graphite. So the question why and how we can grow from only few layers to achieve on larger times to achieve more than 100 layers is not clear yet. And one of the reasons for that could be that the mechanism of growth is by diffusion into the bulk and segregation out, similar to the case of few layers graphene and nickel. But we thought at this time that this is not possible because the solubility of boron, and especially of nitrogen, into nickel, it should be very low. Today, actually, we are changing our opinion about that, and we are still studying that. Other reason could be that somehow the boron and nitrogen species just attach to the edges of the already formed HBN or to defect in the film, so then promoting the growth of additional layers. So we don't know yet what is exactly the mechanism for that. Actually, nobody knows what is the mechanism of growth that these materials grow. Nickel. We can do it on copper. The best results are on nickel. We are working also on copper and platinum, but in this case, nickel. You can show also the increase in the thickness by XPS characterization. And so then we ask, if we can grow so thick materials with very nice planar structure, so what's the role of the substrate? What's the role of the nickel? And so then we try to grow the same films on different materials like sapphire, silicon dioxide, the quartz, etc. And we noticed that we just can't do that. You can see here a cross-section TEM image of a film, of two films that were grown in the same CBD process, one on nickel, one on sapphire. And you can see that on sapphire you have only partial order very close to the surface, but then you have what is usually called in the literature a turbostratic structure, a disordered and nanocrystalline structure. But here on nickel, you have a planar HBN structure almost all over the thickness of the film. But so then we continue to grow HBN by different methodologies. Today, and I will show you in a minute how, we can synthesize very large single crystal domains of HBN, as you can see here. The triangular domains are HBN. The black areas are covered by HBN. The brighter are the exposed nickel. This is a schematic representation of a triangle, an HBN triangle. This is based on theoretical reports showing that the N termination is just more stable than the boron termination. And the way that we do that, and we discovered that, I must say, by coincidence, is by using what we called in the group a nickel pocket. In this case, a nickel pocket, which is a nickel foil, which is folded into a closed pocket. And this methodology we used for a long time to grow very large graphene domains, and it worked very good for graphene, but it didn't work never for HBN. We didn't know then what were why was that. But when I introduced in the pocket some amorphous carbon powder, we noticed that we can get this nice single crystal, large single crystals, which we didn't know that if they are single layer, bilayer, but I will show you in a minute that they are single and bilayer actually. And the reasons for that could be different. By the way, I did this experiment to achieve a different, different thing. I was trying to grow stacked layers of HBN and a few layers of graphene. And I will show you that actually I succeed by different approaches. This is one of them. So the reasons for the growth of HBN so nicely inside the pocket. By the way, outside the pocket we get only thick and disordered HBN. Inside the pocket, the reasons could be the following. One is that the amorphous carbon, acts as a purifier of the gases coming to the chamber. We use ultra-high purity gases, but still they have some impurities in them. And the second possible reason is that the carbon reacts with the hydrogen, which is in the chamber and at high temperature. And so then the hydrocarbon reacts with oxides or other impurities on the surface, so cleans the surface of the nickel, promoting the growth of HBN. Now, we are testing these two possibilities by different methodologies, and I will not talk about all the details. But we don't think that neither of them is the one that explains the results. But we think that might be a third possible reason, is that carbon species that attach to the surface of the nickel acts like anchor points to attach to a B and N species and then acts like nucleation points for further growth of HBN. And we are trying to make some collaboration to explain that, but we are not sure yet what's the reason for that. So I told you that till now we didn't have any way to characterize in a good manner the hexagonal boron nitride in 2 dimensions. The only way till now to, for example, know how many layers you have in the film is by doing TEM. But TEM is very local. So you depend on a good student or that does a very good job and to have some to have some good analysis in 2 dimensions. Here we show that in collaboration with Professor Finstrom from Carnegie Mellon, that we can use a limb to map the number of layers over large areas, over tens and hundreds of microns square. So what you can see here on the left is a typical limb image, limb microscopy image. And here you can see the different spectra for the different points in the limb. So this is the reflectivity of the electron. Okay? So what do you need to look at is at those dips that represent resonant transitions of the electrons between the first BN layer and the nickel, or between BN and BN, different PN layers. And by analyzing the position of these peaks and the number of the peaks, you can in fact map and count the number of layers over a very large areas, as you can see here after analysis. The red is the bilayer, the blue is the single layer areas. Yeah.
So A and E are at the same layer, aren't they?
A and E. Yeah, but look at that. You see this area?
Yeah.
So this area has a two-layer region, according to this analysis.
Oh, I see. Okay.
Yeah.
What are the other curves? B, C, D.
So A, B, C are single layer, D, E, F, double layers. And you can see, this is the same area, by the way. This is the mapping of the same area.
layer have different characteristics than the single layer.
Yeah. In the double layer, you can detect the transition between the BN and BN. What do you don't have in the single layer? You have only one BN layer. And we can show that, in fact, we can synthesize thicker films, as you can see here, by the different methodologies, and we can do the same mapping to count till, in this case, till 6 layers of HBN again over large areas, and that's something that was never shown till now for HBN. For LIM, yeah, it's not good as in the Raman spectroscopy, as you may imagine, but I don't remember exactly. Few microns, I guess. Yeah. This wasn't done by me, by the way. It was done in collaboration with Professor Finster from Carnegie Mellon. Yeah.
So how did they determine, show 6, 5, 4 layers, how was the determination made?
So I will show you for the...
Theoretical analysis of the spectrum, or was it calibrated against some other method?
No, this is from theory. It was shown by... actually, this methodology was developed for graphene on silicon carbide by the same group. That's why I made contact with them. And they can show with theoretical models that the peak at this energy region, it is arising from the transition between the first BN and the surface, in this case nickel. But the lower energy tips arises from the transitions between the BN and the VN. In this case, they show pretty much the same for graphene, few layers of graphene. Now, for graphene, it's not so important because for graphene you have much better ways to do that, much faster and cheaper and easier ways to do that as Raman spectroscopy and mapping. And as I told you, HBN is supposed to be the best support material for graphene devices. So we have made a few attempts to make graphene devices on single crystal triangular HBN domains. As you can see here in this AFM image, you can see the triangular domain and a layer of graphene covering it. And you can see that the transfer wasn't so successful, but even after this bad transfer and with all the wrinkles and bubbles, absorbates, and all you can see there in the AFM, we could achieve mobilities of a few thousands in all the devices, and the few devices that we made by using the synthesized materials. And nobody till now have shown that you can achieve good mobilities using CVD-derived HBN material. So, but we are working on that, and I think that we can improve that. Sorry? Yeah, electromobility. It's not the highest one, of course. We are supposed to get much higher than that. But taking into the account all these wrinkles and absorbates, I'm not surprised that we didn't get the maximum. I'm surprised that we get a few thousands, actually. Actually, we see wrinkles in both, in the HBN and also in the graphene. The HBN was deposited by standard transfer. Yeah, of course. HBN is a wide band. Yeah. I'm sorry. So now that we have good materials, I was interested to see if we can get if we can have another characterization tools to check and to test our materials. So I made contact with Professor Zhang from Texas Tech University, which his group is expert in photoluminescence measurements of wide bandgap materials, and he was interested in doing some measurements on my material with different thicknesses. And as you can see here, at room temperature, even at room temperature, you can see that the position of the emitted peak changes, and that is according to theoretical predictions, actually showing that the bandgap of the HBN actually changes with the number of layers. And moreover, more recently, we could achieve PL measurements from single or bilayer samples, as I showed you before. And this might be the first PL measurements on so thin HBN materials. And as I told you before, we can synthesize stacked layers of HBN and a few layers of graphene. And in this case, I did that by using carbon-enriched nickel that you can prepare by different methodologies, exposing the nickel at high temperature to different carbon sources. And then, before it segregates out to form the graphene, we synthesized the HBN on the surface of the nickel in this case, and then by controlled cooling and segregation, we could form a thin layer of a few layers graphene at the interface between the HBN and the nickel. And that we can show by Raman spectroscopy. Sorry, we did. If we use the C13 enriched hydrocarbon to make the graphene, so you can have the D band, which is very close to the HBN signal. You can have it shifted down, so then you can identify fairly easily between both peaks, which is not trivial and sometimes it's challenging. But moreover, we did also PL measurements on the same samples. So here you can see, for comparison, the spectra that I showed you before. This is for 1 or 2 layers. And this is also for 1 or 2 layers, but on a few layers graphene. So you can see first that we have the same peak. But in this case, there is an additional peak which is related usually to impurities and defects. And so that tells us that during the segregation, and that maybe tells us that during the synthesis of the HBN, we had already some segregation of carbon. So this peak could arise in principle from carbon impurities in the hexagonal boronitride lattice, or from defects or other things. But the point is that the PL measurements could be very useful to characterize to achieve some information on the quality of the HBN that otherwise we don't have any insight from any other characterization tool to know that. And so this is just a very preliminary. We just started to work on MOS2, and so we just started by reproducing some papers that were recently published. We're using solid precursors, but we are building a more sophisticated system to use gas precursors that will allow us much better control on the catalytic decomposition of those gases and precursors to form the different layers. So I will conclude, and then I will move to the research plan. So I would like to point out that the conditions for graphene growth are not entirely understood yet, but we know that there are thermodynamic parameters and kinetic factors that we need to take into account. Solubility might not be the only explanation for the results that we have on the different metals, but also we need to study the surface and the bulk diffusion of the carbon on the surface. And we can, I showed you that we can synthesize graphene, directly deposit graphene on the electric surfaces. We can achieve a nice control over the thickness of the HBM film, and more recently, over the domain size and also the thickness to achieve single layer level HBM. And I would like to thank the people that worked with me. And now I will move to what I think, and what I think it will be interesting to continue and study. So I divided my research plan into three parts that at least the first two are very connected each other. The first one is to develop ways and synthetic methods to grow other to the atomic films on large scale, similar, analogous to the growth of graphene and copper, but to use other materials. And as I showed you before, the list for layered compounds that are available is pretty large and diverse. So then after the synthesis and the study of the growth mechanisms, there is the characterization, and for every material you need to find the set of characterization tools that will give you the right information, and this is not trivial. And then, of course, I guess that after that, some possible applications might appear. The second one is to combine between different atomic films. One way to do that horizontally is by using methodologies of seed growth. You use one type of material as a seed to grow, to continue and grow with a different material. Every color represents a different material. You can do it in principle with a different material, so the same two materials as a superlattice. You can. I would like to also study the growth of stacked films, one on top of the other, as I showed you before for HBN and graphene. And this can be achieved by combining between surface reactions and bulk reactions, like bulk diffusion and segregation, and surface reactions, as I showed you before for HBN and a few layers of graphene. And the third one that is very interesting to me is that you can, in principle, take a thin film of a layered compound. Let's start with the easiest material and the most available material, a thin layer of graphite. Then you can pattern some holes in it, and by selective deposition into the holes, and then growing a different material or the same graphene by diffusion into the bulk of the metal and segregation to the interface, you can grow. In this case, let's say that you grow a graphene or you expose it to hydrocarbon. You can go parallel graphitic layers that will in fact be, depending on the patterning, like nanotubes that are perpendicular and connecting between the layers of graphene, the few layers of graphene. And this is important for many applications. For mechanical applications, graphite is considered a soft material because of the weak interaction between the layers, but also for thermal applications, by controlling the distance between these patterns, you could control the thermal conduction in the vertical direction. And the last one is to use different methodologies and apply some periodic potential on those atomic films. Here you could use a surface reconstruction, like atomic steps or nanofacets that I used in the past for many other applications, or you can use other nanopatterning methodologies to make very local variations in the you can use graphene or other materials, and with this variation you can study them for many applications. First, you can study how these periodic potentials influence the physical properties of these layers, but you can also use them as for points, local points where you can continue and modify very locally those layers to achieve different, many other functionalities. And you can use, in principle, single crystal hexagons, in this case graphene, but you can use single crystal domains of different materials and study how this periodicity influences, how the crystal orientation of the film is in relation to the periodic patterning influence the physical properties. And okay, thank you. I guess that this is another possible applications of these films. Thank you. Thanks.
Some more questions? I have a question, actually. You mentioned in the end templated growth, visible surface.
Okay. I didn't mean the planted growth. I meant to transfer full layers. I mean, to transfer those films to different pre-patterned surfaces.
Oh, I see.
Not to grow them on these surfaces from the beginning. That will be very hard. I wish to have a way to grow graphene on sapphire, or there is no such a way. Believe me, I tried that. It doesn't work.
Okay.
There is another question. What do you mean? Stacked layers of different something?
So there are chemical ways to grow graphene.
Okay. So actually, I mentioned it was in the graph in the beginning. I mean, but I don't know much about that. But I know that by these molecular approaches, you can achieve some very small, very small graphitic domains. I don't know what's the status of these methodologies. Actually, I don't know how is the control over the number of layers, and I don't know much about that. I know that the results are not so good. Till now, that's yeah. Graphene was used as barrier. Actually, you can see it. You could see it in that in the. Like hexagonal boronite or others, not as far as I know. Yeah, I don't know of any work like that, and one of the reasons for that is that graphene is the only 2D layered compound that you can synthesize over large scale at the singular level. It's the only one. Now we are starting to get results on hexagonal boronite, but this is relatively new. We and other groups, we're not the only one. No, hexagonal bore nitride we can grow over large areas, single and bilayer. We don't have a good control over homogeneity yet. We don't know why. And that's it. Other layered compounds, there is no way to grow them at a single layer level, and also when growing them at the few layers level, they usually appear first at single domains with different number of layers, but then they merge together to form an homogeneous film. There's no way. Graphene is the only material right now that can be synthesized at the single layer level very consistently. Okay, I don't know of any work like that. I guess that they can be. I mean, some of. Yeah. I know that for graphene, many people did that. I guess that you can use hexagonal bore nitride as well. I don't know about the stability of other layered compounds. That's also something that you need to check. Yeah.
Can you go back to the slide of the band structure of graphene?
Yeah. The first one, the introduction.
Yeah. So when you reduce the dimensionality, and you get this bottom side effect of opening the band, so what happens is just these two cones just
separate each other.
Don't change, then themselves remain the same. Sorry?
Like in nanotubes. You know what's happening in nanotubes, right? It's like the semiconductor nanotubes, where you have. You ask about bilayer or nanoribbons? You ask about nanoribbons.
Just the effect that opening of the band gap.
With nanoribbons, not with bilayer and electrical field. It's me?
So?
I think that what's happening is similar to the case of a semiconductor. No, actually, it can't be the same. Because in semiconductor nanotubes, you have a standing wave that introduces. It's a boundary condition that forms a standing wave, I guess, right? So then introduces like slices, perpendicular cross sections here to these cones. So then, if those slices are exactly at the Dirac point, you're still in the metallic mode. This is what happens with metallic nanotubes, carbon nanotubes. But if those slices are not exactly at the Dirac point, at the K point, sorry, not the Dirac point. So then you actually, it's like you said, it's like you separate, and the actual band gap, the actual band structure is the one that is a bit separated, and that's why the band gap is formed, right, Amir?
What does it mean? It also affects the effective one?
Yes.
Okay, if there are no more questions on the same area again.
Thank you. אוי, נזכרתי עכשיו שלא חזרנו על השאלות.
היא סימנה לי, אבל בזה היה מאוחר מדי.
תודה, ביי.